All right, so SN1 reactions have a carbocation intermediate, and a more stable intermediate generally leads to a faster reaction. So we have a lower energy intermediate. It's going to have a lower energy of activation to get there usually, and that would mean a faster reaction. And the high energy intermediate in SN1 is that carbocation. So it's the carbocation. And this is kind of along the lines of page 11 of your notes, but essentially that intermediate is stabilized by something called hyperconjugation. So we'll try that here. Stabilized by hyperconjugation. And essentially that's the CH sigma bond that is adjacent to the open p orbital is able to delocalize electron density onto it. And I'll draw it up here, but I'm going to show it as I have it in the notes as well. But essentially, this secondary carbocation here, if we turn it from being in the plane to the side like this, it would look like this, where we have the empty p orbital that has a positive charge. We turned it like that, so we have a wedge to a hydrogen, a dash to a CH3, and then the other CH3s in the plane. And essentially, the CH bonds that are in the same plane as the carbocation will essentially lend some of their electron density to that empty orbital, and that stabilizes it. So essentially, we can draw that sp3 orbital, and we'll just kind of draw some dotted lines showing that it is giving away some of its electron density to stabilize that positive charge. And that's what I have in your note packet too, right here. So essentially we see that a primary carbocation over here has no opportunity for that hyperconjugation because there are no CH bonds out here, versus the secondary carbocation that we have right here has the CH3 that is essentially looking exactly like I put up on the board, but also this other CH3 is doing the exact same thing. It's just harder to show it since it's no longer in the plane with that carbocation. And essentially what we see is that going from a methyl carbocation to a primary carbocation to a secondary carbocation to a tertiary carbocation, it gets more stable as we get more substituents off of that positive charge. So I'm going to draw that up on the board as well. So if we have just a CH3 plus versus a plus next to a CH3 versus a secondary, so this is a methyl carbocation, this is a primary carbocation, this would be a secondary carbocation, and this is a tertiary carbocation. And I often put C plus for carbocation. It gets more and more stable this way, so it's more stable. And so much so that it turns out that these two do not do no SN1 reactions. You have to have at least two groups hyperconjugating onto yourself for this SN1 reaction to be possible. So more on that in 1 minute. All right, so which of these SN1 reactions would we expect to proceed the fastest? And I already mentioned that the high energy intermediate, that carbocation, it can't form if it's primary or methyl. So both of these, if we can imagine the iodide leaving in both of these cases, we would form a methyl, just a CH3 plus, if that iodide left. This iodide left, we'd have it just attached to a CH, so we have a CH2 and a CH3, so we'd only have one group hyperconjugating. Both of these are going to lead to no reaction. So essentially, we can't form a carbocation if we don't have at least two groups hyperconjugating. So we might as well write that here too. no C plus on primary carbocations. These two can form a carbocation, but just as the secondary is more stable than the primary because two methyl groups are hyperconjugating, the tertiary is going to be the most stable, having three different groups hyperconjugating onto itself. So this will be the fastest. And again, why is that? That's because it has the most stable carbocation. Because it would have three different CH3s hyperconjugating onto itself, stabilizing it. So that kind of finishes out our full description of SN1 reactions. And now we're going to talk about, well, how can we tell if a reaction is going to proceed by an SN1 or an SN2 mechanism? So that's where we're going.